before we continue with the first set of problems, we need to know a little bit about. Okay, we need to know a little bit about decimal numbers. So there are three types of decimal numbers: terminating decimals, non-terminating decimals, okay, and non-terminating and non-recurring decimals. Terminating decimals, non-terminating but recurring decimals, and non-terminating and non-recurring decimals. Okay, so we look at the first one first, non-terminating decimal. Sorry, terminating decimals. So for example, I have 1 over 2. 1 over 2, I can write it as 0.5. Okay, there is no other digit after 5. So therefore, this is terminating. It has stopped here. Therefore, this number is known as terminating decimal. Okay, 3 over 4 is also equivalent to 0.75. Since there's no other digit after 5, this number is also known as a terminating decimal. Okay, so all terminating decimals can be written as a fraction p over q. If they can be written as a fraction p over q, therefore they are all rational numbers, correct? Yes? So all terminating decimals are rational numbers. Okay, so number 2 is non-terminating but recurring decimals. Example, 1 over 3 is equals to 0.33333 and so on. Okay, so the 3, it doesn't stop, it continues. Therefore, it is known as non-terminating. But if you look at the digits here, they are all repeating, recurring. 3, again 3, again 3, again 3. So 3 is repeating. If 3 is repeating, this decimal can also be written as 0.3 and we put a bar on top of 3. This means that the digit 3 is repeating. So this is a non-terminating but recurring decimal. But you can write it as a fraction p over q. Therefore, non-terminating but recurring decimals are all rational numbers. Okay. The third type of decimal numbers are non-terminating and non-recurring decimals. Example, say E, this is 2.718281828 and so on. Or we have pi, okay, 3.1515926535 and so on. If you look at the digits at the back behind the decimal, they are continuous. There's no ending. Okay, and the digits do not repeat. There is no repeat. If you look carefully, none of the digits repeat. So this decimal is known as non-terminating and non-recurring decimals. Okay. Another example is square root 2, 1.414213562 and so on. So we know all these numbers are irrational numbers. Okay. Why? Because they cannot be written in the form of a fraction. So, do you understand the three types of decimal numbers now? Yes?
Yes.
Yes, madam.
Okay, so now we can continue with our problem solving questions. Okay, first problem. Okay, prove that 3 over 4 is a rational number. How do we prove that 3 over 4 is a rational number? Okay, one method is we can change 3 over 4 into its decimal. So it becomes 0.75. Is this, what kind of a decimal is this?
Terminating.
Yes, it is a terminating decimal. Okay, because it is a terminating decimal, therefore 0.75 can be written as fraction p over q. Therefore, it is a rational number. Okay, so that is how we prove whether a fraction is a rational number or not. Okay, so problem 2. is 0.09, there's a bar on top here, okay? Is 0.09 bar here a rational number? Is this a rational number? We need to justify if this is a rational number, okay? So how do we do this, okay? So let's say, okay, let's say that x is equals to 0.09. Repeating means which number is repeating? 9. So we can say, sorry, this is repeating, huh? This whole thing is repeating, okay? 09. So 09, 09, 09, and so on, right? So let's say x is this, okay? And this is our first equation, okay? So now we want to move the decimal point to where the repeating numbers stop, to the first set of repeating numbers. So how many spaces must we move? 09, 09, 09. So if we move 2 decimal points, we will cover the first repeating numbers, correct? So we want to take equation 1, okay? Equation 1 multiplied by 100. Because we move 2 spaces, so we multiply by 100. Therefore, we get 100x is equals to 9.0909. Correct? Yes? So because here we have 6 digits behind the decimal, so we can add 6 digits here. So it doesn't matter because it is continuing. Okay? So then, so this is our equation 2. Now equation 2 minus equation 1. What do we get? So we got 100x minus x is equal to 9.090909 minus 0.090909. So what do we get here? 100 minus x is 99x. 99x is equals to all this minus off. So 9 minus 0, 9. So x is equals to 9 over 99, which is this. We can simplify this. It becomes 1 over 11. Then x is 1 over 11. So we have written 0.090909 as a rational number. Okay? Can I understand that?
Not really.
Not really. Okay, so we have the number x, right? We have x is equals to 0.090909. Okay? Now we want to write this in the form of a rational number. So we know that these numbers are repeating. 09 is repeating, 09 is repeating, 09 is repeating. So we need to move this decimal to the first set of repeating numbers here. We need to move the decimal here after 9 here. So to move the decimal, we need to multiply by 100. So if we multiply equation 1 with 100, we get this, okay? So now when we minus equation 2 minus equation 1, we only, what is left is only the integer. Everything behind the decimal is gone already, okay? So because only the integer is left, we can write it as a fraction, okay? Okay, let's see one more problem, similar problem, huh? Okay, problem 3, yeah? Is this number 0.1232323 a rational number? Okay, so we always start like this, okay? Let's say x is equals to 0.1232323, okay? So now, what should we do first? Where do we want, which numbers are repeating?
After 3.
After 3, right? So if we want to write this number again, we can write it like this, 0.123, and above the 23, we put a bar, which means that 23 will keep on repeating, okay? So we need to move our decimal point here, 1, 2, 3. So we need to multiply by?
1000.
Correct. So if this is our equation 1, so equation 1 multiplied by 1000, we get 1000x is equals to 123.2323. We add another 23 Okay, this is our equation 2. Now what do we do? Can we minus this? Okay, say we minus this. Okay, so equation 2 minus equation 1. Let's see what we get. Okay, so we have 1000x minus x is equals to 123.232323 minus 0.123323. Can we minus this? We will still have digits behind the decimal, right? Because this is 1, 2, 3. Up here is 2, 3, 2, 3. So how can we overcome this problem? What must we do? So we cannot do like this first, okay? There's one more step that we have to do here. What should we do? Now we have to multiply again. We have to, before we go further, okay, 1 minute. Okay, so equation 1, we multiplied by 10. We need another equation. So we have 10x, equation 1 here, multiplied by 10. So we have 10x. So we are going to move this one space. Multiplied by 10, so it's one space. So it is 1.232323. So this is our equation 3. Now equation 3 minus equation 2. What do we have? 1000x minus 10x is equals to 123.232323 minus 1.232323. Now when we minus, everything behind the decimal point disappears, right? So what do we have here? 1000 minus 10?
922.
Okay, equals to
122.
122. Therefore, x is equals to 122 over 990. If we simplify this, we get, 61 over 495. So we have managed to write this decimal number as a fraction, P over Q. Therefore, this is a rational number. Okay, so when you want to convert decimals into rational numbers, this is the way we do it. Okay. Okay, now we're moving on to a different type of problems. Okay, so before we do this problem, we need to understand what are Egyptian fractions. Okay, the Egyptians of 3000 BC, they had a very interesting way of writing fractions. They were able to write any fraction as a sum of unit fractions. Okay, they wrote any fraction as a sum of unit fractions where all the unit fractions were different. For example, 3 over 4, they wrote it like this, 1 over 2 plus 1 over 4. These are two different unit fractions. 6 over 7 is 1 over 2 plus 1 over 3 plus 1 over 42. 12 over 13, they wrote it like this, 1 over 2 plus 1 over 3 plus 1 over 12 plus 1 over 156. There can be other combinations, but they are all unit fractions and they are all different. So we are going to do some problems concerning Egyptian fractions. Okay, before we go to that, we want to revise what are unit fractions. So unit fractions are fractions that has a numerator of 1. For example, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and so on. Okay? So what is the largest unit fraction? Anybody?
1 over 2.
Which one is bigger? Is this big? Yes, 1 over 2 is the biggest unit fraction. So that means it is going this way, it is descending. That means 1 over 3 is less than 1 over 2. 1 over 4 is less than 1 over 3. 1 over 5 is less than 1 over 4. 1 over 2 is the biggest unit fraction. Okay. So 1 over 2 can also be written as the largest unit fraction less than 1/2 is 1/3. So it can be written as 1/3 plus another unit fraction. How do we find this unit fraction? We minus these two. 1/2 minus 1/3 is 3 minus 1/6. So 1/2 can also be written as 1/3 plus 1/6. 1/3 can be written as the next largest, biggest fraction that is smaller than 1/3 is 1/4. 1/4 plus another fraction. How do you find this fraction? 1/3 minus 1/4. This is LCM 12 divided by 3. 4 minus 3 is 1/12. So 1/3 can be written as 1/4 plus 1/12. 1/4 is equivalent to the next unit fraction next to 1/4 is 1/5 plus, how do we get the fraction? 1/5 minus 1/4 minus 1/5, this is 20 LCM divided by 4. 5 minus 4 is 1/20. So it's plus 1/20. So you see a pattern here. What if I have 1/n? So how do I find this fraction? What fraction will be here?
1/n plus 1.
Plus 1.
Yes, 1/n plus 1. Plus, what will be the next fraction? Do you see a pattern here?
1/n times n plus 1.
Yes, correct. Because 2 times 3 is 6, 3 times 4 is 12, 4 times 5 is 20. So here we will times n plus 1. Very good. Okay. So if you see here, this is one method of writing unit fractions as a sum of other unit fractions. Okay. This formula only works for a unit fraction. Okay. Normally, this formula is given like this. 1/a is equals to 1/a. This is how you will see it in other books, okay? Plus 1 plus 1/a into a plus 1. Instead of n, we're using a. That means any unit fraction, for example, 1/7, I can write it as the sum of unit fractions. So 1/7 will be 1/a plus 1 will be 8. Plus, now your a is 7. So a plus 1 is 8. Plus 1/56.
57.
56. Okay, correct. You multiplied it 56. See? So very easily we can write 1/7 as a sum of two different fractions. Okay? So this is what Egyptian fractions are all about. Egyptian fractions are how you can write fractions as a sum of unit fractions only. They don't use other fractions. Okay, why do they do that? Okay, let's just see one reason why we use Egyptian fractions. Okay, Egyptians, they use unit fractions in their daily life. For example, we see this situation here. Maria has 5 loaves of bread which she wants to share between 8 of her mates. How much does each mate get? So she has 5 loaves of bread. What is your answer actually? You have 5 loaves and you want to share between 8 people. So what is your answer?
5/8.
Yes, correct. We would straight away say it is 5/8. But practically to cut each loaf into 8 parts and then count 5 parts and give each person is quite difficult to do. That is why the Egyptians, their mathematics is very practical. So what they do is they take the first loaf, divide by 2, divide by 2, divide by 2, divide by 2. So this half give to the first person, this half second person, third person, fourth person, fifth, sixth, 7, 8. So 4 loaves finished already. How much did each mate get so far?
1 each.
Are you sure? How many people are there? 8. Take 1 loaf, cut into 2. This half give 1 person, this half give 1 person. This half give 1 person, this half give 1 person. This half give to the 5th person, this half give the 6th person, this half 7th person, this half 8th person. So how much did each mate receive so far?
1/2.
1/2.
Half of
Okay, correct. 1 over 2. So far, each one has got half of a loaf of bread. Now you have one more and you have 8 maids. So you need to they divide this into 8 parts. 8 parts. Sorry. And so one part is, what's the fraction for one part? 1 over
1 over 8.
8. So therefore, each maid gets 1/2 plus 1/8. So this is how they work out their fractions. This is how they divide, actually divide. Okay, half, 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 and then give everybody 1/8 more. Okay, so that is how Egyptian fractions came about, and it is really quite useful. This we use this in daily life, although we don't realize that it is Egyptian fractions. Okay, okay. Now we're going to solve some problems regarding Egyptian fractions. Okay, let's start with this. How would an Egyptian represent 4 over 5? How would you represent 4 over 5? Okay, because we Egyptians, they only use unit fractions. So we must rewrite this as the sum of unit fractions. And we are going to use the greedy algorithm. Okay, so let's start with 4 over 5. Okay, now what is the biggest unit fraction that is less than 4 over 5? If this is a number line 0, 1, the middle is half, right? Is 4 over 5 bigger than half or less than half?
Less than half.
Okay, 4 over 5. What is the half of 5? What is half of 5? What is half of 5?
2.5.
Yes, 2.5. 2.5 is half of 5. Now, is 4 over 5 bigger than half or less than half?
Bigger than half.
Yes, 4.5 is bigger than half. So the largest unit fraction less than 4.5 is half, isn't it? Okay, so we are going to write this as 4 over 5 is equals to 1 over 2 plus another fraction. So what is this fraction? How do we find this fraction? 4 over 5 minus 1 over 2 is equals to, LCM here is 10, divided by 5 is 2, 8, minus 5 is 3 over 10. So this is 3 over 10. Okay, but this is still, 3 over 10 is still not a unit fraction. So we must change this. So 3 over 10, what is the largest unit fraction less than 3 over 10? Our unit fractions are 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, and so on. Okay, so can we use half?
No.
Half is too big, right?
Yes.
Yeah, so if we minus, we will get a negative number here. Can we use 1 over 3? If we use 1 over 3, 3 times 3 is 9. 9 minus 10 is also negative. So we use 1 over 4.
5.
Okay, so
Oh,
this is
4.
1 over 4 plus another fraction here. Let's try this. Okay, so 3 over 10 minus 1 over 4 is equals to 40. So this is 12 minus 10 is 2 over 40. 2 over 40, we simplify, it becomes 1 over 20. So this is 1 over 20. When you see a unit fraction here, okay, then we straight away stop. We don't have to continue anymore. So therefore, 4 over 5 is equivalent to, what are all the unit fractions that you see here? 1 over 2 plus 1 over 4 plus 1 over 20. Okay, so this is the greedy algorithm. You take away, they call it greedy because you take away the highest unit fraction. You keep on doing that until you reach all your fractions. Okay, can understand? Okay, a bit difficult maybe, yeah? So I'll do another problem for you. We do another example. Express 9 over 11 as an Egyptian fractions. Okay, so we are going to change it to unit fractions, like this. Okay, so we are going to start with 9 over 11. So ask yourself first, is 9 over 11 greater than half?
Yes.
Okay, so we start with half. Okay, so half plus what fraction? So how do we find that out? 9 over 11 minus
1 over
half.
2.
How much is this?
22, 9, 18,
17 over 22. Can we simplify this? No. Okay. So we write our answer here, 17 over 22.
22.
This half is unit fraction, but 17 over 22 is not unit fraction. So we have to change 17 over 22. So 17 over 22 is,
7.
sorry, 7.
Yes,
Huh?
yes.
Yeah, 7. I'm sorry. Thank you for telling me that. Huh?
7.
Okay, 7 over 22. Okay. So now we want to change 7 over 22. This is less than half. Okay. So if we use 1 over 3, 3 times 7 is 21, and 21 minus 22 is negative. Okay. So we can't use 1 over 3. So we must use the next fraction, that is 1 over 4. Okay. So how do we find the remainder? What's the next fraction? 7 over 22 minus 1 over 24. So this is 88. 88 divided by 22 is 4. 4 times 7 is 28. Minus 88 divided by 4 is 22. 22 times 1, 22. So this is 6 over 88. Simplify this, we get 3 over 44. So this is 3 over 44. Still not a unit fraction. So change 3 over 44. So okay, what's the fraction that we are going to use now? If we use 1 over 4, 4 times 3 is only 12. 12 minus 44 is a negative number. So what fraction can we use here? Can anyone suggest a fraction?
1.6.
1 over 6? 6 times 3 is 18. Still small because we want to minus this fraction, okay? So here,
1 over
we
8.
want to get something more than 44. So what fraction can we use? 1 over 15.
1 over
Okay.
15.
Because 15 times 3 is 45. Okay. Okay, I'll show you why it's 1 over 15. So 3 over 44 minus 1 over 15 will be,
1 over 660.
yeah, 660. So this is 45 minus 44 is 1 over 660. Unit fraction, right? So we can
Yeah.
stop here.
Stop.
Okay, so this is 1 over 660. Sometimes you will see some large numbers, especially the last fraction. Huh? So therefore, 9 over 11 is equals to 1 over 2 plus 1 over 4 plus 1 over 15 plus 1 over 660. All the unit fractions here. Okay. So this is what is equal to. This is how they write it out. Lah. So your problem, as I see it, is only how to determine this fraction. Okay. So normally the first 3 lines will be all the small unit fractions. And then when you come to this, how do you choose this unit fraction? When you cross multiply here, okay, when that number must be bigger than this number. Okay, slightly bigger, that's all. As long as you can minus. If it's smaller, then you can't use lah. Okay. So this is the greedy algorithm to change fractions, normal common fractions into Egyptian fractions. Okay. So far, okay?
Yes.
Okay, now
Okay,
let's
madam.
okay, now let's continue with one more. Okay. This is a different method that I'm going to show you. Later I'll show you a much easier method, okay? So actually there are many methods for you to do this, okay? These are just some of the very common methods. Huh? Okay, we want to express 8 over 11 as an Egyptian fraction. Now we're going to use the algebra identity method. Huh? Okay, so this method, the formula is like this. Huh? A over AB minus 1 is equals to 1 over B plus 1 over B into AB minus 1. Okay, so we are going to use this method. So we need to change 8 over 11. Okay, so we want to write 8 over 11 in this form. Can we write in this form? It will be 8 over 11. Can we write in AB minus 1? It will be, say we need 12 right here. Because we need 11, we need 11 here, and here we know there's a minus 1. So that means this number must be a 12, cannot be any other number. 12 minus 1 will give you 11. And 12, we want to write it as a product of two numbers, okay? AB. So maybe we can write 2 times 6 minus 1, okay? But here, the formula says A over AB. So this A and this A should be same. But here we don't have any similar numbers. So we can't use this. So what we should do, we must break down 8 over 11. So 8 over 11 is also equals to 6 over 11 plus 2 over 11. Okay. So we do one by one. Okay. So first we do for 6 over 11. So 6 over 11 is also equals to 6 over 2 times 6 minus 1. Okay. So we have written in the form of A over AB minus 1. So this is, we're going to follow this. So this equals to 1 over B. What is our B now? From here, what's our B?
6. 6.
On top is A. So A is 6.
6.
B is 2. Okay, yeah. So 1 over 2 plus 1 over B is 2 into AB minus 1. AB minus 1. How much is this whole thing? 11, right? AB minus 1 is, you can write here AB minus 1. That is 2 into 6 minus 1. But you know that 2 into 6 minus 1 is the same as 11. So you straight away write there 11. Okay, so straight away write there 11. 2 times 11. So this is 1 over 2 plus 1 over 22. So 6 over 11 is 1 over 2 plus 1 over 22. Then we have a next fraction here, which is 2 over 11. So 2 over 11 is equals to 2 over, write it in the same method. Okay. Okay, now you compare with the formula here. So this, now your A is
2.
2 and your B is
6.
yeah, so you write this 1 over 6 plus 1 over 6 times 11. So this is 1 over 6 plus 1 over 66. So it's 2 over 11 is 1 over 6 plus 1 over 66. Therefore, 8 over 11 is, we know the 8 over 11 is 6 over 11 plus 2 over 11. And 6 over 11, we have broken it down to 1 over 2 plus 1 over 22 plus 2 over 11 is 1 over 6 plus 1 over 66. So that's our answer. So which method do you prefer? Is this more difficult or is the other one more difficult?
This one.
Okay.
More difficult.
Actually, you can mix and you can do, okay? You can mix, you can start with this method and then halfway you can change and continue with greedy algorithm, or you can start with greedy algorithm and you can change. Okay. Okay, I'm going to show you one more method. Okay, this one is much easier. I'm going to show you this. Okay, it is called the split method. Split method. So 3 over 7, we know it's equals to 1 over 7 plus 1 over 7 plus 1 over 7, correct? Is this an Egyptian algorithm? Are these Egyptian fractions?
Yes.
Yes?
No.
No, why no?
Because they are all same number. Same fraction.
Yes, they must be different fractions. Although they are all unit fractions, they are all the same. Okay, Egyptian fractions are distinct. Distinct unit fractions. That means different unit fractions. Okay, all must be unit fractions and they must all be different. So we start from here. 1 over 7 we can use is the first one. So this 1 over 7, can we change this into another sum of unit fractions? We know this formula, remember, 1 over A is 1 over A plus 1 plus 1 over A times A plus 1. So 1 over 7 change using this formula. What do we get?
1 over 8.
Yes, plus?
1 over 7 times 8.
Yes, correct. 7 times 8, 1 over 56. So we have this 1 over 7 now. Now we still have two same ones. So we have to change the last one, okay? So this one is already done. So change the last one. 1 over 7 is?
1 over 8.
Yeah, correct. It is still the same. 1 over 8 plus 1 over 56. So now we have 2 1 over 8 and we have 2 1 over 56, right? Okay, let's
Yeah.
change 1 over 8 first. Okay, this 1 over 8, let's change it to, we can change this using this formula. We can change 1 over 8 to 1 over
9.
9 plus
1 over 64.
uh,
8
8
times
times 9, 72.
22.
Okay, but correct. The method is correct. Okay, plus 1 over 56. This 1 over 8 we can leave, right? Because now we go no more 1 over 8 yet. This 1 over 8 we can leave. Okay, this 1 over 56 we must change. We change it to using this formula. So this will be 1 over 57 plus 1 over, if you times 57 times 56, you get 3092. Okay, so now we can, to make it easier, we can rearrange it. 1 over 7 plus 1 over 8 plus 1 over 9 plus 1 over 57 plus 1 over 72 plus 1 over 3192. Okay, is this method easy? Much easier?
Yes.
Yes. Okay, so this is how you change common fraction to Egyptian fractions. Okay, so a lot of problems concern Egyptian fractions when it comes to rational numbers. Okay, to understand rational numbers, we must be able to do all these things. Okay, then we know clearly what rational numbers consist of. Okay, so we have come. Okay, I have one more. Sorry, I have one more question for you. Okay, this question is actually in your tutorial. It's already in your tutorial, but I'm just going to show you how to do the first part. After that, you can continue yourself. Okay. Okay, let's look at this question. A quantity and its 2/3 and its half and its 1/7 together make 33. Find the quantity. Okay, so we want to change this into mathematical sentence so that we can find the answer. So what is a quantity? How can we represent a quantity?
X.
Yes, very good. A quantity is X. Okay, so we have a quantity X. And how do we write and? Plus, okay, its 2/3. How do we represent that? Its 2/3. You know what is 2/3? Tell me what is 2/3. 2 over 3. Yes. So what is whose 2/3? Its 2/3 is whose?
X.
Yeah. So it's 2/3 of X. So plus 2/3 of X, and its half
Plus
plus
1 over X.
1 over 2 X plus its 1/7.
1 over 7.
Yes. Together make.
33.
That means together make 33. That means
Equal
equals
to
to 33. Correct. Now how do we solve this? What is the LCM? 42. Okay, so 42 divided by 1 is 42. This is 42x. 42 divided by 3. 14 times 2, 28x plus 42 divided by 2 is 21. So this is 21x plus 6x is equals to 33. So we have 97x is equals to 1386. X is equals to 1386 over 97. Okay, so we have got the quantity. But now they ask you, how might the Egyptians have written the answer? So now you must change this into Egyptian fractions. Okay, this is the second part. Okay, so this you can continue in your tutorial. Okay, I just shown you how to do the first part.